Hey there, fellow space cadets. Welcome to the mind-blowing world of quantum field theory, where the universe reveals its most bizarre and beautiful secrets. It's a journey into the very fabric of reality, where particles pop in and out of existence like cosmic fireflies. Quantum field theory is the language we use to understand the universe at its most fundamental level. It's the marriage of quantum mechanics, which governs the microscopic world of atoms and particles, and special relativity, Einstein's masterpiece that describes the relationship between space, time, and the speed of light. But hold on tight, because quantum field theory takes us beyond the familiar realm of everyday experience. It's a place where particles aren't tiny billiard balls, but rather ripples in quantum fields that permeate all of space and time. Ready to dive in? Let's go. Before we can wrap our heads around quantum fields, let's take a step back and talk about classical fields. Imagine a calm lake on a windless day. Now toss a pebble into the water. What happens? That's right, you get ripples spreading outward from the point of impact. These ripples are disturbances in the surface of the water, and they carry energy and momentum as they travel. That, my friends, is a classical field in action. In classical physics, fields are continuous and smooth, like the surface of our lake. But in the quantum world, things get a bit more interesting. And by interesting, I mean mind-boggling. In quantum field theory, we ditch the smooth, continuous fields of classical physics and replace them with something far more bizarre: quantum fields. These fields are not smooth and continuous but rather quantized, meaning they can only exist in discrete chunks of energy called quanta. Think of it like a digital image. Zoom in close enough and you'll see that the seemingly smooth image is actually made up of tiny squares called pixels. In a similar way, quantum fields are made up of these fundamental quanta. And guess what? These quanta are the particles we know and love. For example, the quanta of the electromagnetic field are photons, the particles of light. The quanta of the electron field are, you guessed it, electrons. But here's where things get really wild. In quantum field theory, particles aren't just ripples in quantum fields. They are the fields themselves, constantly interacting and influencing each other. It's a cosmic dance of creation and annihilation, where particles pop in and out of existence like subatomic fireflies. Intrigued? Let's see how this plays out with Dirac's belt trick. Section 4. Dirac's belt trick, untangling the quantum knot. Hold on to your hats, folks, because we're about to enter the strange and wonderful world of Dirac's belt trick. No, it's not a magic trick, but it might as well be. This mind-bending concept helps us understand how particles behave in the quantum world. Imagine a belt looped around a fixed object. Now twist the belt 360 degrees. You can't untwist the belt without either detaching it from the object or rotating it another 360 degrees. This is Dirac's belt trick in action. In quantum field theory, this trick helps explain the strange behavior of particles like electrons. Electrons have a property called spin, which is quantized, meaning it can only take on specific discrete values. Dirac's belt trick demonstrates that electrons need to be rotated not once but twice 720 degrees to return to their original state. This seemingly simple observation has profound implications for our understanding of the universe. It helps explain why matter is stable, why particles have antiparticles, and even sheds light on the nature of black holes. Who knew a simple belt could unlock such profound secrets? Section 5. Lagrangians, the action heroes of physics. Now let's talk about Lagrangians, the unsung heroes of physics. In quantum field theory, Lagrangians are mathematical expressions that encode the dynamics of a system. They tell us how things move and interact over time. Think of a Lagrangian as a recipe for a physical system. It lists all the ingredients, fields, and the instructions, equations of motion, for how these ingredients interact to create the final product, the physical system. But Lagrangians are much more than just recipes. They are powerful tools that allow us to calculate how particles will behave in different situations. By minimizing the action, a quantity derived from the Lagrangian, we can determine the most likely path a particle will take. It's like finding the shortest route on a map, except instead of roads, we're navigating the intricate landscape of quantum fields.